Hi everyone, I'm just going to run through week 2 notes for EPMATH134. So this week we're doing arithmetic of whole numbers and we're doing it all through algorithms. So algorithms are these formalized arrangements that we use to add, subtract, multiply and divide that, if an answer is possible, will always give us the answer. So it's a set of rules in each case, and we will have done them all before, but it could have been a while. Okay, so let's just start with an addition algorithm. So we've got one there already. Let's just look through it for starters. 654 plus 753. Okay, so 3 out of 4 of our algorithms are right aligned, as in we start from the right and move left, which is unusual for us. We read left to right, obviously. But multiplication, subtraction, and addition are all right aligned. Division, at least, is left aligned. But we start at the right and add the units. 4 plus 3 is just 7, straightforward. The 5 plus 5 is 10, but what we actually do there, I don't have room to put a 2-digit number here. I don't write it there. I put the 0 down and put the 1 there. We call that a crutch figure. Now what I've really done, we don't have to go there, but what we've really done, that's a 50 really, that's a 50. I got an answer of 100, so I put 0 in the tens column and 1 is saved here in the hundreds column to add up with them, because it just tacked another 100 onto the answer. But the beauty of all of these algorithms means we can do them all as single digit operations. So I can just think 5 plus 5 is 10, put down the units part, carry the tens part. And then 6 plus 1 is 7, plus that 7 is 14. I'd carry the 1 if there were more numbers, but there aren't, so I just write down the number. So 1407. Not too many traps in these. One thing with the addition algorithms is we can have many rows. I mean, I can do, let's make some numbers a bit larger, and 8 for 8. So I can do, yep, so 6 and 7 and 8, well, I like to pair them up, anything that pairs up nicely. 8 and 7, 15, we've got a 21. Okay, 1 down, the 2 goes up, and it still reads 21. It still makes sense to me to write it that direction. The 8 and 2 was a 10, plus the 5 and 4 was a 9, so I've got 19. 9 down, carry the 1. We've got 2 9s there as 18. We've got 3 9s in total, so we'll go straight to 27. Put down the 7, I would have carried the 2, but nothing to carry it with, so 2 7 9 1. So addition, yeah, pretty nice. Let's move to the next one, subtraction. Now there's 2 main methods for subtraction, and there's what I've referred to here as old school and new school. Now if you had primary school roughly before the early 90s, you would have learnt the way I learnt it, which was this: 556 minus 249. So 556 minus 249, well, my method was doing this, the way I was taught, was 6 minus 9 is an issue. Now be careful, it's very easy to see a lot of people write 3 here, because they just swap the numbers. A 6, a 9 and a minus sign makes 3. But no, the order clearly matters. It's top minus bottom. And if you're going to get a negative answer, we've got to do something else, because our algorithms don't deal with negatives. So our method here is I'm going to turn the 6 into a 16 by doing that. Now I can't just add that 10 out of the blue. What we do in the old method is add a 1 there in the tens column. So what I've done is I've added a 10 to this number, and I've added a 10 in the tens column here. So why am I allowed to do that? Let's just check the concept of equal addition. I think we might have looked at it last week. But the concept of equal addition says, I'll write it here, 7 minus 4 equals 3. Hopefully we're all in agreement there. What if I add a 10 to both numbers taking part in subtraction? It's still 3. What if I add an extra 200 to both numbers in the subtraction? The answer is still 3. That's the concept of equal addition. I can add anything I want to both numbers involved in the subtraction, and the answer remains the same. So when I added a 10 here, really in total that's become 566, really. The bottom one, I've got an extra 10 here, so really that's 566 minus 259. But that's okay, because the answer is going to be the same. The 16 minus 9 is a 7. I'll stop there for a second and say, look, do your subtractions however you want. I like the count on method, as in I walk from 9 to 16. I just think, look, it's 1 step to 10, it's 6 steps to 16. So looking at that, the answer to that is 1 plus 6. Okay, I'll say that a few times because I think it just, I don't know, I find it easier 5 minus a total of 5 now is 0, and 5 minus 2 is 3. Notice slight variation that this was taught was instead of putting a 1 there, some people cross out the 4 and put a 5, but it's exactly the same concept. So there's the old school method, which we call equal addition. The new school method is trading, which is 556 minus 249. By the way, when I talked about schooling in the early 90s, I was just talking about New South Wales there, the changes we made. Now, okay, again, I can't do 6 minus 9 because we don't do with negatives. I want to turn that into a 16, but what we do in this new trading method is that 5 really represents 5 tens. So if I take the 5 down 1 to 4 tens, where's that 10 I just got rid of? Well, I only got rid of it to there. So if I think in single digits, I've turned the 5 into a 4 and a 1. If I think what I really did, I turned the 50 into 40 and a 10. So now it's a 16 minus 9, it's a 4 minus 4, and it's a 5 minus 2. I mean, I didn't like that at first, because the top one was my method. But it was changed because it was considered a nicer way than trying to explain that, look, we might have changed the question here, but it's still the same answer. We didn't have this concept here. The only concept we've done here is turn a 50 into a 40 and a 10. And I agree that I'd rather teach that concept to a child than, hey, look, I can add 10 here and still get the same. So anyway, so that's it. Now, if you're asked in this course to do a subtraction, do it any way you want. But it's important to understand both algorithms because it's just, well, we're here to understand maths, and it's important to understand the concept of equal addition because of last week's mental arithmetic, and this trading method. They're just two very good methods. Now, I should do another example, probably of each. I'll do one without 0, then I'll do one with 0. So just some random example here. I'll do 435 minus 249, and I'll do that for both. So 435 minus 249. If I use the old method, the equal addition method, 5 minus 9 is a problem, so instantly I'm going to change it to a 15 and put a 1 in this column to subtract the 10 I just added, basically. And I'm going to walk from 9 to 15, that's 1 step plus 5 steps, that's 6 steps. 3 minus what's now a total of 5 is not doable without negatives either. I want you to be a 13, so I'm going to put that there and that there. So it's really 13 minus a total of 5, which is 8. Again, I'm walking from 5 to 13 by going 5 steps and 3 steps. 5 to 10 is 5. 10 to 13 is 3. 4 minus a 3, good odd 1. Okay, there's the old method. The new method is 5 minus 9, like we said, the problem. Steal off the 3, take it back to a 2 and put the 1 there, which is 15 minus 9, which is a 6. Now 2 minus 4 is a problem, so I'll steal off the 4, take it back to a 3, and the 1 I nicked goes there. 12 minus 4 is 8. Again, I'm walking 6 steps to 10 and 2 steps to 12. That's a 6 plus 2. And 3 minus 2 is 1. So there's the methods, either which you can use to calculate, but we should understand the concept of both. Now on the next page, we've got, well, what if there's a 0 in there? Changes things a bit. Let's just check. 304 minus 157. Well, the equal addition method, the old school, is putting 4 minus 7 is a problem. Fine. Dash, dash. They're really 1s. 14 minus 7 is 7. Again, I can't do 0 minus a total of 6. So I'll put the 1 there and the 1 there in the next column. So it becomes 10 minus 6 is 4. And 3 minus a total of 2 is 1. So that 0 actually changed nothing in the way to approach the new method. But with the old method. But with the new method, trading, when I come to steal off a 0, I panic a bit. Okay, I can't. Right here, I want to steal off this 0, take it down 1 to give myself a 10. But I can't steal off a 0. But that's okay. Instead of looking at just what's to the left of the 4, it's a 0. Well, look bigger. It's actually a 30. It's 30 tens. So I can steal off the 30, take the 30 down to a 29, and the 1 I nicked goes there. So it's still the same, and I know some students cross off the 3, take it back 1, and the 0 crosses off and becomes 9. I just like crossing out the whole number, because 30, take off 1, is clearly 29. There's no need to explain why do noughts become 9s. Well, it's just the number prior to it. So 14 minus 7, 9 minus 5, and 2 minus 1. Yeah, and just to check on a larger trap here, It didn't affect us in the old method. What if there was a stack of zeros? Well, it's no biggie. If it was 70,006, say, minus 1, 2, 3, 5, 7, then once we've done the initial step, it actually gets easier, because 6 minus 7 is a problem. So I look to the left of the 6 and I see an entire 7,000 tens. So 7,000 becomes 6,999 tens, and there's the one I nicked. So 16 minus 7, well, that's 3 plus 6. 9 minus 5 is 4, 9 minus 3 is 6, 9 minus 2 is 7, and 6 minus 1 is 5. Okay, move on to long multiplication now. We'll use the white space on the next page. And picture. Let's grab that one. So we've got all those steps there, but it's going to be much easier to talk it through than it was to both write it and probably even worse to read it. Okay, now actually first pretend the 2 and the 6 isn't even there. If I press this button, will it erase? Ooh, nice. Okay, I'm just going to do this first and then I'll erase it, then I'll do the big one. The point I want to make is we went straight for the jugular in this question. We went for a 3-digit by 3-digit. We didn't do any simple examples, so let's try this simple example. All I've got to do is distribute that 7 amongst the 3, the 5 and the 4. Really what we're going to do is work out, well, what's 7 3s? It's going to be a 21. 7 50s is going to be 350, and 7 400s is going to be 2,800. But again, we don't have to deal in more than single-digit multiplications in algorithms. I'll just say 7 3s are 21. I'll put down the unit and carry the tens to be added to the answer in the tens column. Okay? Because I'm now in this column, that counters for the fact that the 5 is actually in the tens column. I don't have to think about zeros. I just got to go 7 5s is 35, plus that 2 carried over is 37. Put down the 7, carry the 3. Now I've just got to do 7 4s is 28, plus the 3 is 31. Okay, so that was it. I didn't physically see the 2,800, the 350, and the 21. There is another multiplication method where you do that, but no, this is our standard long multiplication, and we'll go with this. Now, it's not really the question at the right. Let's just build it up. What if the question was actually had a 6 there? Well, I would have done everything the same to the first thing. I would have started with a 7 and done exactly what we did. That's 7 times 453, as it says down there. But okay, now let's do the 6. Let's get rid of the crutch figures. They were from before. Now if I'm going to use the 6, this is where I do have to take the 0 into account, because the first operation isn't 6 3s, it's 60 by 3. So the answer should be 180, not just 18. But if I put a 0 there, that means that when I write down my 18, it's 180. So I just have to remember, if I move to that second digit, that I've got to put a 0 here. And soon, clearly, I'll introduce a third digit, and I'm going to have 2 zeros on the next line. So that 0's to count for this is really 60. Now 6 3s are 18. 8 down, carry the 1. 6 5s are 30, plus that 1. Am I putting my hand over the... it doesn't matter. It's probably a good thing. 6 5s is 30, plus the 1 is 31. Carry that up there somewhere. And the 6 4s are 24, plus the 3 is 27. Again, like in addition, when there's no more numbers up here, you don't carry the number up there, you just write it down. So far so good. Now, if it was just that, I would add up these two answers. Okay, if it was just 67 times 453, I'd put a line there and add them up. But let's expand. We'll go, yep, it's really a 267. Get rid of the crutch figures from before. It's really a 200, so I picture this as like a triangle of zeros that forms. I'd keep going if we had more digits. But we don't. 2 3s are 6. 2 5s is 10. 0 down, 1 up. And 2 4s is 8, plus the 1 is 9. Now I'll add them all up. 1 0 0 is 1, 8 7, that's 15, 6 7 8 9, 3 7 is 10, 0 down, 1 up, and there it adds up to a 12. So I get an answer of 120,951. In my 3 rows, I did 7 453s, then 60 453s was that, and then 200 453s was that, as written down here. Okay, I might do one more long multiplication just for practice. I'll probably the slow way, but just rub all this out. Go. Yeah, that's good. Oh, don't stop. Why? There we go. Okay, this is good viewing. Okay, just make up another 3-digit. 327 times 482. That'll do. Okay, the 2 7s is 14. Put down the 4, carry the 1. So I always focus on this number first. Okay, 2 2s are 4, plus that 1 is 5, and the 2 3s are 6. Okay, first row is done. I've done with the 2. I'm also done with that crutch figure. I don't want to accidentally use it again. I move to the 8. Oh, David. It's not really an 8, it's an 80, so I've got to remember that triangle of zeros. Let's remind ourselves fully, so I don't forget. Not that I was going to. 8 7s is 56. 6 down, 5 up. 8 2s are 16, plus that 5 is 21. So the units part there, the tens part there. And the 3 8s is 24, plus 2 is 26. Now I've already got my 2 zeros there for the 400. I'm done with the 8. Done with them. 4 7s are 28. 8 down, 2 up. 4 2s are 8 plus 2, 9, 10. So I put the 0 down and the 1 up. And now 4 3s are 12 plus that 1 is 13. Ooh. Okay. Now 4 0 0 is 4. 5 6 0 is 11. 8 9 10, that's 16. 6 and 1 is 7. 2 and 3 is 5. 157,614. Okay, great. Hopefully. What do we got next? Page up. Okay, we start with short division. Now, short division, most people prefer short division over long division. Well, the numbers are smaller, but long division we need to know, okay? We will specifically get asked questions. Use long division to do this. And if you learn long division, it's much easier doing it than if you did the same question with short division. But I'll show you. Firstly, short division. Now, I like to think of this as backwards. When the question says, like I've written here, 123 divided by 4, the algorithm is backwards, as in the 123 moves to the right and the 4 moves to the left. So it's backwards, but at least we're going left to right now. And this question wasn't done there, but let's look at it. 4s, how many 4s can I get out of a 1? Of course I can't get any 4s out of a 1. And I think writing that 0 is really important because it keeps things aligned, and I would definitely recommend, even though in the long run the answer doesn't need a 0 at the front, I strongly recommend you write it to keep in your columns. Now I haven't used that 1 yet. I didn't take any 4s away from the 1, so the 1 is still effectively a remainder. It's remaining there. It's still there, and I've got to move to the 2 now. So I read that as a 12. How many 4s can I get out of a 12? I know I've seen some people will cross it out and put a little 1 there. As long as you're reading the next question is 12, it's all good. So 4s out of a 12 is 3 with no remainder, so I put nothing here. So now my next question is how many 4s can I get out of a 3? Very easy again, like subtraction, to swap these in the head and think how many 3s out of a 4. I can do that. No, we're taking 4s out of a 3. So I can't get any 4s out of a 3. So what's left? There was a 3 there. I took no 4s away from it. It's still a 3. So answer is 30, remainder 3. And note that that's a big OR. You can write your remainder as 3/4. When we get to fractions, that's the way we'd want you to write it, and we'll have questions that request, after we've done fractions, request you to write it in that format. But at the moment, since we haven't done fractions, it's just not critical whether you write R3 or write 3/4. So let's look at this other short division down here. It was 693 divided by 5. So left to right, how many 5s can I get out of 6? I can get 1 5 out of a 6 with 1 left over. 5s out of a 19, well I checked through my 5 times table. 4 5s is 20, but I can't take 20 out of 19. So 4 5s is too many, 3 5s is good. 3 5s is 15, the gap between 19 and 15, well that's 4. Leave me with how many 5s can I get out of 43? 9 5s are 45, that's too much. 8 5s is 40, yes I can get 40 out of 43. Leaving me 3 remainder. 40 taken off 43 is a 3 remainder. So again, remainder 3 or 3/5 would be acceptable. Just an explanation, even though I said we don't need this yet. Why are we putting it over 5? Everything in 693 just got divided by 5, and there's the answer. The 3 didn't get divided by 5, it got left over. But it should still be divided by 5. This entire number was divided by 5. So we get the answer, and even the remainder got divided by 5. Next one, okay, long division. Well, I've got an example there, and I'll do it both long and short division. I'll write here that it's 46 and the number being divided is 6738. And I'll just put over here, I'll do it down here, a short division version. And you'll see it's the same, it's just harder to do, because short division you've got to do a lot of stuff in your head that you don't have to in long division. So let's go to the long. The first question is, how many 46s can I get out of a 6? So of course, traditionally we use long division when there's a 2-digit divisor, the number dividing. Well, if it's 2-digit we use long, if it's 1-digit we use short. Truth is, you could use either for both, but just the numbers get harder, and when the numbers are harder, that's when long division's an advantage. But anyway, if I've got a 2-digit number, I'm clearly never going to get a 2-digit number out of a 1-digit number, so we're always starting with noughts with these. 46s out of a 67. Well, I can see that 2 46s would be, 92, at least 80 something. That'd be too many. Only 1 46. Now the big difference here, if I was doing short division, I still would have started the same way, but in short division now I'm doing 67 minus 46 in my head. And that's a bit rough. We can get there. I can see that, okay, well, it's going to be a gap of 21, and then I would write the 21 there, and my next question would be how many 46s out of a 213. Okay, but it's just harder. What we do in long division is, what is 146? We write it down. Instead of doing 67 minus 46 in my head, I do it on paper, and I find that much easier. 7 minus 6 is 1, 6 minus 4 is 2. It's not always going to be as nice as that, but do the subtraction any way you want, and there it is. Now, and then the difference is, instead of 21 being written next to the 3, the 2 1's here, and 3 goes down to meet it. So whenever you get a remainder in long division, you bring down the next number. So now 46 is into 213, I need to do a few times tables. I could have written my 46 times tables down here, but I'm not going to bother in this question. I'm just going to, check them. And what's some ballpark figures? I know 10 46 would be 460, so 5 would be half that, 230. I reckon 4. Let's just check. 46 by 4 would be 6 4s is 24. Carry the 2. We've got 16, 17, 18. And let's just confirm what I said before, that I reckon 46 times 5 is 230. 5 6s are 30. 4 5s is 20 plus, yeah, it's 230. So clearly I can get 184 out. I can't get 230 out of 213. So the answer is 446 is 184. Again, subtraction happens on this. Do your trading method, do your equal addition algorithm, or even my method. My method, I walk 16 steps to get to 200, and then 13 more steps to get to 213. So I'm thinking 16 plus 13 is 29. Okay, but each to their own. I've got a remainder, so bring down the next number. Now I've got to get up to 298. Well, if 5 46s were 230, add another 46 to that. 276, that must be 6 6s. 6 46s, I can't talk. So, what if I added another 46 to that? No, I'm over 300. 6 is going to be the answer. 6 46s is 276. Add another 46 in that, and I'll get over this number. And no, we need something that can be removed from 298. So now I do my subtraction. This one's a nice one. 8 minus 6 is 2. 9 minus 7 is 2. And 2 minus 2 is 0. I've got no more numbers to bring down, so that's my final remainder. I either write remainder 22, because, as I said, we're not into fractions yet, or I could have written 22 over 46, or I could have written 11 over 23. If you're a fraction person, you'll know what I'm doing. But yeah, I just simplified. I just, divided the top by 2 and divided the bottom by 2. I saw a common factor of 2. Okay, let's do one more short division. Long division, sorry. Can I do it on the next page? Is there a next one? Yeah, I'll use this page. Now here's one I prepared earlier just because it ends up with a 0 in it. I just don't want it to be off-putting. 3, 6, 8, 0, 5. I'm not referring to the question having a 0 in it. That's no biggie. The answer has a 0 in it. Okay, and it's only divided by 12, so our 12 times tables might be better. They might not. Not everyone's got their times tables, but let's go for it. 12's out of a 3, of course not. 12's out of a 36. Well, 3 12s is exactly 36, so yeah, I can do that. And again, it's long division. So we write it down. 3 12s is 36, and the remainder is, of course, 0. Now I bring down the 8. This is what I'm talking about. That, alright, I've got a remainder. I brought down the next number, and I'm asking how many 12s can I get out of an 8. and I can't get any 12s out of an 8. That's totally acceptable answer. There's zeros in numbers, okay? So yeah, if you ever say none, well, that's fine, just put the 0. What do I do now? Well, we do as we always do. When I've got a remainder and I can't get anything out of it, I bring down the next number. So we've spent, you know, longer than normal on this line, but that's the way it goes. How many 12s in an 80? Well, I know 5 12s are 60. I know 6 12s are 72, and 7 12s is 84. 84 is too much. 6 12s are 72, as good as I'll get. 80 minus 72 is just an 8. Again, I just walked from 72 to 80. Last number to bring down is a 5. Check my 12 times tables. I said before 7 12s was 84. That's as good as I'll get. Leaves a remainder of 1. And so I either write R1 or R1 on 12. It's nice to get in the habit of the fractions, because it's only week 3 fractions anyway. Yeah, I hope that helped. Okay, see ya.